All right, so this video is pretty much an introduction to redox reactions, which we kind of saw a little bit about, but with alkenes, alkynes, and then compounds with CX bonds, so where X is a more electronegative atom. So I have methane drawn here, basically the most reduced carbon that you can get, carbon compound that you can get, and the oxidation and reduction process are represented by an oxygen in brackets, oxidation, and then reduction, H in brackets. So if you go from methane to methanol, you're removing a hydrogen bond, a carbon-hydrogen bond, and replacing it with an CO bond. And then you can move forward from there and oxidize methanol to form a compound, this carbonyl compound here called formaldehyde. And we essentially removed a carbon hydrogen bond, and then created another CO bond, right? Formaldehyde, you might be familiar with formaldehyde, as it preserves like animals, or I don't know, live things. I lost the word right now. Let me make this smaller so I can fit everything in one. So, yep. Yep. Sweet. All right, sweet. So now this compound right here, we did again remove a carbon hydrogen bond and then create another CO bond. And so that's, again, we're just oxidizing methane all the way to methanol formaldehyde. And then this carbonyl compound with the OH is called formic acid. And when we oxidize that, we remove a carbon-hydrogen bond and create an additional carbon-oxygen bond. That gives us carbon dioxide in the end, okay? And so this process is really all about removing the carbon-hydrogen bond and then creating a carbon-oxygen bond. And also, it just works out in the way that it does, where you have a CO single bond, CO double bond, CO single bond, CO double bond, because carbon needs to have 4 bonds, right? So let's remove that hydrogen, and then we create another carbon-oxygen bond. Okay, let's do oxidation again. Remove that hydrogen, create a carbon-oxygen bond, right? So we can do it one more time. Remove that last hydrogen there, right here, and create another carbon-oxygen bond. Okay, so I'm running through this just because, first of all, the process I find really interesting, but also I just feel like it's really easy to follow, but I want to make sure that I'm not kind of oversimplifying it. So I really want to just make sure that you understand the process of just really removing hydrogen, creating a carbon-oxygen bond. And then the reduction is literally the opposite. So you're moving in the opposite direction, where you add so you remove a carbon-oxygen bond and then you add a hydrogen bond, a CH bond. And so that's why we go from 1 hydrogen to 2 hydrogens, and then moving from formaldehyde to methanol, we have 3 hydrogens. And then finally, in the end, we get to methane, where carbon has 4 hydrogens. And so that's, we draw them as an equilibrium, and in theory they're not an equilibrium necessarily. But you can go forward and you can go backwards. Just depends on, you have to use certain reagents, and those reagents are what we're going to go over in this video. But first, I want to tell you a little something about methanol and moonshine. Methanol will kill you straight up, make you go night night forever, because it forms in your body formaldehyde and formic acid. And I told you formaldehyde preserves tissue, and then formic acid is like a red ant bite. So it does not feel good. And having a large amount in your body is really bad. Formaldehyde is also carcinogenic. So you can imagine if it preserves tissue, then it's probably not good to have in your body. But ethanol, on the other hand, let's draw ethanol oxidation process. We form this aldehyde species, which is called acetaldehyde. And then if we oxidize acetaldehyde, what we get is, so remember, removing that carbon-hydrogen bond and creating a carbon-oxygen bond, we get acetic acid, which is just vinegar. So you get red ant bites and like tissue preserving material in your body. Not good. And the other, acetaldehyde's not ideal in the body, but then you get acetic acid is pretty much kombucha. So enjoy. That's why ethanol is not as toxic to the body. It is, of course, toxic because the acetaldehyde in large quantities is not good either. But anyway, just some fun facts I kind of wanted to show you. All right, and so we've seen this kind of oxidation and reduction process tallied up in previous chapters. Remember, oxidation was the increase in the number of CZ bonds, where Z is like a more electronegative atom, as well as a decrease in the number of CH bonds. Okay, well, let me make this red because I made it red above. So, bada bing, bada boom. All right, now let's make the reduction process blue. Reduction is, again, just the exact opposite. It's a, decrease in the number of CZ bonds, and then an increase in the number of CH bonds. All right, so increase the number of CH bonds, and that's pretty much redox reactions in a nutshell. So that's the process that we're hoping to achieve with a variety of oxidizing agents and reducing agents. So let's go over the reducing agents first. There's essentially 3 different categories, I guess, maybe not even categories, just different types. But again, if it's a reducing agent, we want to reduce it, and so that means we're kind of going from right to left on that flow chart, if you will. That's increasing the number of CH bonds, and the way we're going to do that is by adding H minus, so hydrides. And we've seen hydrides before, so that hydroboration reaction, and that's almost what we're going to use here. We're going to use sodium borohydride, which is NaBH4, and then when lithium aluminum hydride, which is AlH4. Okay, that's one way. H2 with some metal catalyst, such as palladium, platinum, or nickel, is another method of reducing like alkenes, for example. And then we can have H2 with a palladium, so a metal catalyst, but it's different than the palladium above. It's palladium on calcium carbonate with lead acetate, so lead OCOCH3. So you can also abbreviate acetate as OAC. And then that also has quinoline. So quinoline is 2 fused rings together. One is a heterocycle, and it's got a nitrogen in there. And so that's essentially the palladium catalyst above is really super strong, and then this palladium with lead and quinoline is what we would call a poisoned catalyst, and so it's less reactive. Okay, and this is pretty much what that lead acetate would look like with 2 of them on there, except I just drew the one for you. Okay, not super important that you know necessarily the structure, but it is important that you know it's called Lindlar's catalyst and that it is less reactive, and it's because it's quote unquote poisoned with lead acetate and quinoline. Okay, now the last category, like I said, is using sodium metal and ammonia, so NH3. I don't want you to confuse this for NaNH2, which was sodium amide, which NaNH2 was a super strong base, right? So Na metal and NH3 ammonia. So we'll go into detail for all of those guys in just a second, but let's do reduction of alkenes first. Now, reduction of alkenes in general is just adding CH bonds, right? And so I mentioned above that you can do that in a variety of ways, but super common way is using metal catalysts with such as palladium, nickel, or platinum. Super common one that you'll see like in your textbooks are like PD-C or /C. That's literally palladium on carbon. So it's kind of like carbon palladium mixed together, and then you get the syn addition of those 2 hydrogens like that. Okay. Let's do a couple more just to kind of give you a look at it. So we have another, this would be butene with H2. I'm putting it over the reaction arrow just so you can get another look at kind of how it might be presented. And palladium slash C, palladium slash carbon, palladium on carbon to make butane. Okay, all we're doing is adding hydrogens, right? So this one right here, this dimethylcyclohexene, is going to add the H2 across that double bond, but since I mentioned above that it is a syn addition, we actually do care about stereochemistry now, and we have to have both of those hydrogens as a wedge or a dash, and that's important, okay? Syn addition. So we're adding, the reason why this happens is because the alkene is approaching the palladium carbon surface because it is solid material. So it has to approach it on one surface. So imagine it, alkene kind of sitting on your table, and then you add hydrogens from your table. And so it can only be on one side. Okay. I'll get into more kind of a mechanism for that in a little bit. But I just want to mention one thing that we have seen before again, catalytic hydrogenation. So now catalytic hydrogenation might seem a little bit that like vocabulary is somewhat new, but hydrogenation is not. So the cis-2-butene and trans-2-butene reactions, we did reduce these to make butane, before, and this was used as an explanation as to why like proof that the trans alkene was more stable, because we had the heats of hydrogenation values minus 120 kilojoules per mole for the cis butene, and then minus 115 kilojoules per mole for the trans. The fact that negative 115 is lower means that it was lower in energy to start, and because less energy was released and to get to the same endpoint. And so therefore the trans was a more stable alkene starting material. Okay, so we did see that before. We're just kind of introducing that again. Okay. All right, let's talk about this mechanism real quick for the catalytic hydrogenation of an alkene. Okay, so remember, a catalyst is when you add, we're adding a metal catalyst because we're adding a very small amount of palladium on carbon, and it's going to be more or less reused over and over again. Okay. As opposed to the hydrogen, which is added in stoichiometric amounts to add to every single alkene molecule in there. So that alkene approaches this palladium on carbon surface. That's supposed to be a dotted line here. And then we have a bunch of hydrogens kind of like poking up, okay? And that hydrogen, those hydrogens are bound to the palladium metal center, and then they undergo a reaction with the alkene and essentially add to the alkene to make the alkane final product. And again, this is why it's syn addition, because it's like the hydrogens have to kind of approach the alkene from the same surface because it is an actual surface, and it's only being added from one direction. But in inorganic chemistry, you draw it differently, and maybe this will be a little bit more helpful in understanding, but it's actually a mechanism for the most part. You have a cycle, more or less is what it's called. So we have H2 approaching palladium. H2 adds to the palladium and breaking that hydrogen-hydrogen bond, and then you have the alkene approaching the palladium now, and then the hydrogen adds to one of those alkenes, and now the carbon is bound to palladium. So it might be confusing. You don't need to know this mechanism. I'm doing this just so you can better understand what's going on. And now that's because that hydrogen added to the far carbon, and that carbon needs 4 bonds, so it's bound to palladium now, right? And then now what we've done is we added a carbon-hydrogen bond again to get to that final product, and then we end up with the original palladium metal, and then we can basically start over again, right? That's why it's a cycle, and that's why palladium is a catalyst. So imagine this area right here didn't have hydrogens, but it had R groups in the pink. those R groups are going to kind of essentially take up space and perhaps affect the rate of reactivity, right? And so, again, an overarching trend in organic chemistry is sterics and steric hindrance, right? And so it reduces the rate of reactivity. So what we're going to have here is mono to di to tri to tetrasubstituted alkenes, and me struggling with this rectangle here. Sorry, I'm trying to make an arrow. You know how I do. All right, so let's just, we're not going to touch that. Okay, so we've got a trend going from left to right. We have an increasing number of alkyl substituents. And then what do you think the trend is for rate of reactivity? As we go from left to right, we are decreasing the reactivity rate for reduction of that alkene, okay? And that's again because of steric hindrance. It's much easier to approach a metal center and then kind of have the reduction process occur when you have less stuff going on that carbon, okay? And so there are additional hydrogenation reactions that we should be familiar with. They are more or less the same process, but we're going to kind of categorize them because I know sometimes it gets weird kind of translating the reaction products when we only saw the alkene. Let's say, for example, now we got to translate that to the alkyne. So let's do H2 palladium on carbon. Let's say we added one equivalent. So we only added like one molecule of H2 for that one alkyne. In theory, since it is a syn addition of the hydrogen, we would get a cis alkene, right? Because of that syn addition. Now, let's say we added an additional hydrogen and palladium on carbon. So we got one equivalent again. What we end up getting is that alkane product, right? Well, going from the alkyne to the alkane is a super fast process, okay? I mean, like as fast as like the fastest elephant you've ever seen running in pink chucks. Like that's how fast I'm talking about. Like, what? Isn't that adorable? An elephant running in pink chucks? That's awesome. Anyway, that's a uncontrollably fast reaction, and you're not isolating that middle cis alkene product, okay? There's other ways to maybe isolate an alkene intermediate, and we'll go over those in a different video. But for now, just know that if you have palladium on carbon with hydrogen, you cannot control it. You're going to go from the alkyne to the alkane. If you have an aldehyde or a ketone with hydrogen and palladium on carbon, you will do pretty much the same thing that you would do for an alkene, which is add a hydrogen to those atoms that are in that pi bond, so the carbon and the oxygen in this case. And I'll try and draw them in blue just to give you an idea as to, so stereochemistry does matter, right? Because it is a syn addition. So we're going to get the methyl and the hydrogen kind of projected out at us, while the two blue ones are away from us. Obviously that OH can kind of rotate, and so that's why I don't have a wedge or a dash on that. But that's it for I mean, that's analogous to an alkene, and so that's all we have to draw. And just know that alkenes and aldehydes reacting with palladium on carbon, that's kind of a unique process, okay? So just remember that's something you can do. Okay, so now we're talking about triacylglycerols. Why would we talk about those? So remember before we talked about fats and we talked about oils, right? So remember that our group for fats had few degrees of unsaturation, meaning it had a lot of hydrogens and not very many, if any, double bonds. Whereas the oils had lots of DUs, and that affected their physical state. So fats were solid and oils were liquid because they had more pi bonds. So let's talk about that creamy peanut butter, for example. If you got like the OG kind where you got the oil sitting on the top, then that's just natural peanut oils. But if you have Jiffy or Jif or Peter Pan or whatever, I don't know, solid peanut butter like this, then I got the sad face going for you, because you have partially hydrogenated oils, and those oils have been undergone a chemical reaction. So they took those oils and they hydrogenated them, meaning they took these cis alkenes and they added hydrogens to them. So partially means not all of them. So you might have one, two, like a couple there, right? But for the most part, they've brought down the number of DUs, and that's why it's no longer a liquid anymore. It's a solid, because it's more like fats, right? But the reason why this is not necessarily good, partially hydrogenated fats are bad for you, because going back to this catalytic cycle, if we add the alkene, and we already added those hydrogens to that palladium, now we've got one hydrogen added to that alkene, and we got that carbon palladium bond with the hydrogen on there. But let's say we rotated that carbon-carbon bond, so we get the R group not pointed on the same side as the other R, but opposite of it. Okay, so what we're getting now is this palladium with the hydride still there, and then the R groups are opposite of one another or trans to one another, right? So let's say rather than adding that last palladium hydrogen, or that hydrogen from there, we remove the hydrogen that we just added, but it's in a different orientation now. And so what we end up getting is an alkene that is not cis anymore, but is trans. Trans fats are what we just created. No, mama, no. Ah. I like Fresh Prince a lot, guys. I don't know if you knew that by now, but yes. Anyway, we are forming trans fats because that's why partially hydrogenated fats are bad for you, because they are going to contain trans fats as a byproduct of this catalytic hydrogenation process. Okay, so now you know. Probably the most important aspect of this video is trans fats gets you solid peanut butter instead of that oily stuff that'll kind of ruin your shirts and your pants. I don't know about you. Many shirts have gone down with a little peanut oil on there. But anyway, also Fresh Prince, one of the best shows in the 90s. Sorry, bye.